Okay, you can see this is a readable clear text, and the flag is here. So you can imagine if you don't know this tool and you try to write some script by yourself, you may spend like 10 minutes and 20 minutes to solve this kind of puzzles. But if you know this tool, you can solve it in seconds.
Yeah.
So next one, finally we'll come to the modern part. The most familiar and most, wow, the color, nice. The most familiar modern crypto appear in CTF and also in the textbook is RSA. So this is the algorithm for RSA on the t-shirt. It's actually very simple and beautiful. We can see that we construct big N, which is product of two primes P and Q, and then we just choose an arbitrary E for encryption key, and we can use this relationship to find the modular inverse of E, which is D, the decryption key, and then this C is ciphertext. We can just use the nth message we want to encrypt. Okay. Nth message we want to encrypt. We do this calculation to find the ciphertext, and also we can decrypt from the ciphertext to the message itself. So for this kind of RSA problem in CTF, many times we're given those N, P, Q, E, B, C, N, like this, one. This is a CTF that's large. We can see that we're given the N and the E. E is the encryption key. N is so these two become is a pair known as public key, and this C is ciphertext. What we want to do is try to find the private key from the public key and decrypt the ciphertext to find the effect. Before I solve this puzzle, I want to introduce the common RSA vulnerabilities appearing in CTF applications. The first kind is just to factorize that N. We can see that if we know the PQ, we can use this relation to find the D if we know E, because this is just find the modular inverse using Euclidean algorithm. And to factorize the big N, there's a website called FactorDB. It stored a lot of non-factorized big N, and also somebody find that if the difference between P and Q is too large or too small, it will be very easy to factorize the N. And also, if the given exponential, the E and the D, one of them is too small, there are some vulnerabilities. And also, there are some common factor and congruence modular vulnerabilities using some theorems like Chinese Riemannian theorems. But to solve those kind of problems in CTF, actually we don't need to know all those theorems. We just need to know one tool is enough. So this one is called RSA CTF tool. It actually gathered all those kind of possible weak RSA vulnerabilities in itself. And let's see how to use it to solve this problem. Before we solve it, we first want to guess what kind of vulnerabilities is this it exists in this RSA problem. We find that comparing to this table, we find that the E we're given is something like 6, 5, 5, 3, 7 is not too small. And also, we expect D will not be too small. And also, the N, we don't know if we can factorize that N, so we can try these two methods. And for those two methods, we don't find a pair of different N or different E. So our only method is to factorize that N. So let's try. First, we open the factor DB. And copy this N. But this N is in hexadecimal, so we want to first convert it to decimal value. We use Python. Okay, this count to convert it to decimal and paste it here. Yes, we can find the factorization in this database. But we'll not use this result to write our own scripts. We'll just use the tool I mentioned here. First, let's see the usage of this tool. By the way, most of the tools are included in this talk and in the list are open source project. You can find them on GitHub. So the basic usage is first, we use this generate public key comment to generate a public key from the given N and E. And the second step is to use that public key generated to try to find the private key. And if we can find the private key, we can certainly decipher the ciphered text. So first, create the public key. Okay. I write it to the RSA to the top. This is a generated public key. The second step is to try to find the private key. Okay, let it run for a while. Okay, we examine that this private key can be found. So final step is just to decipher this ciphertext. But we find that the input of this Python tool is a ciphered file. So we should convert this hex string into a binary file. Also use the Python script already made it. This one. This is a ciphertext one here. And we just simply use some functions to write it to a file. And then we can try to decipher it on cipher. Okay, wait. You can see the deciphered clear text is just that. So this is the RSA demo. The last problem I want to introduce for modern crypto is length extension attack. And the corresponding tool is the hash pump. First, I will introduce what is length extension attack and what can we employ it in CTF. So the hash function are usually used to generate signatures. Here, the H, the bit H is a hash function, and the secret is secret key. The message is just append to the tail of the secret key, and the signature is generated by it's just a hash of this string. So, what can we? Why do we need the signature? Because if somebody just write a message and he don't want anybody to alter the message, he will use his own secret key and this hash function to generate a signature. And the receiver will verify the signature, whether this signature has been changed. If the signature has been changed, then that means somebody has altered the message. Because anyone don't know the secret key cannot generate a new signature for a different message. But by doing length extension attack, if we know the length of the secret key and given any message we want to append to the original message, we can calculate the correct signature of this message. Let's look at a more real example. I'll not do demo for this tool, but you can find a demo in its usage document. Here, the signature is this string, and the data is these parameters. This is the parameters we usually see in the HTTP URL. And what we want to append, the little m, the message we want to append is this one. And we specify the key length is 14. Assume that we know the key length. And we can see that a new signature is generated. This signature is for this message we forged. You can see it appends a lot of null bytes. And what we can achieve by this attack is that, for example, originally the parameter waffle is equal to equal, and now we append another waffle is equal to leech. So now we overwrite the value of this parameter. This has many applications in CTF. The author of this tool have listed some CTF right up here. You may check it later. Let's continue. Next part is binary. First category of problem in binary is reverse engineering. Actually, last time, there's another speaker have already spoken about tools like IDA Pro and basic knowledge about some binary exploits. This time I'll try to make this part short. First tool I will introduce is that one. That is for PE info extract and also try to unpack the exe file. Let me show you a demo. Here, this is a CTF puzzle. The name crack me. It wants you to crack it. So let's try just randomly input some number. So it tells me the number is incorrect. So what this problem has to do is to find the correct password, and the correct password itself is a flag. So even this exe file, what we want to do is just open it using IDA to try to see the disassembled code. this one is the same. These two are same. We can see they are the same. But this one is packed by me using this famous UPX hacker. We try to open the packed version using IDA. You see that it notifies us that this portable file can be analyzed by IDA. We can see that the function lists have only a few functions. It's not normal, so we know that this one is packed. But how do we know which packer is used to use this tool? We just drag this packed onto this program, this tool, and we find that it lists the info of the packer, the UPX packer. And it also tells me that how to unpack this file. So let's try it. This is the UPX. Successful. Let's try to close it. Let's try to open it with IDEA again.